Dear friends, so we will start with the first session of this course, the fiber optic technology and overview. So I will discuss in this session what are the developments and different potentials of optical fiber technology, and I will in this session I will just give the overview. Then in the continuing session we will discuss in detail the different aspects or in depth the different principles of this optical fiber technology. So this is the content outline of my lecture. So we will start. I will cover what is fiber optic technology, why we need the optical transmission, why optical fibers are required, what are the optical communication systems, and what is the potential of this system. Then of course fiber optics sensing and medical application.
सर मैं काम कर रही हूँ, मैं उधर बोल के आ रही हूँ कि मैं ऑनलाइन वर्कशॉप अटेंड कर रही हूँ, कॉन्फ्रेंस, तो मैं नहीं आ सकती, है ना? बोला तो मेरे को ठीक लग रहा है ये।
आ जाओ।
ये कहाँ से आया मजोत?
बैठे बना बैठे बैठे।
तो ओके।
मैं आता हूँ।
तो फिर आप ही बोलो, आप बोलोगे क्या?
नहीं वो तो आप ही को मजा पड़ेगा।
मजोत को हमारे लिए मैसेज है। So these are the content outline of this this session. So fiber optic technology, it is also called light wave technology. So there it uses light as the primary medium to carry information. So basically this communication is covered under the fiber optics. The general branch is the fiber optics, and we know the optics is the study of light and through free space or through different media, but fiber optics is the study of light propagation in fiber. So when I say fiber, we understand the fiber, it is a very thin and flexible. Similarly, our optical fiber. So we study the propagation of light in very thin media. So it is a primary media to carry the information. Of course, the major application of optical fiber technology is the communication. It has number of applications. Communication is the one of them. In fact, the technology gained importance because of the communication, because of the potential it offers. And other applications are in different areas. We will discuss at the later stage. So it uses light as a primary medium to carry information. The light is guided through optical fibers. So in order to transport the light from one place to another place, we use the optical fiber. So it is a point-to-point link. It is not just like other microwave. Wireless is not as practical as a point-to-point link. Of course, wireless optical is also possible. We call it as free space optics. But there are certain limitations, there are certain drawbacks that it is not adopted, and optical fiber, they are used as a point-to-point link. Most applications uses invisible light, infrared light, specifically in the region of 1310 or 1550. So we use the light sources as LEDs or laser diodes or injection laser diodes. So we need very specific source and specific type of optical fiber. So this is the fiber optic technology. We call it the light wave, because it is the wave propagation which is important. Our optical sources, they behave as they are quantum in nature, but the light propagation, it is a wave propagation. So also called light wave technology. So by fiber optic technology, if you look at some past 30 years, you see there are the remarkable and dramatic changes took place in the electronic communication industry. So initially, there is a phenomenal increase in voice, data, and video communication. Earlier, the requirement was only the voice communication. No, it is not the same thing. Now, the communication requirements are both the voice, data, and video communication, and it demands for larger capacity. So when we are clubbing all these type of information on a same channel, the capacity, large capacity is required. And also more important is more economical communication system. The system has to be economical. Then only the technology will prosper. Then only it will be adopted by masses. In the present scenario, the service provider, there is a competitive market. You cannot enhance the cost of communication. So as a result, we need a very economical system, and it is only possible if the technology reaches to masses. If you take the case of mobile communication, some 20 years before, the mobile was a very important gadget and very expensive. Now it is with everyone, even everybody, everybody has the mobile now. So it and the demand and the cost has come down because it has been adopted by the masses. So this is only the possibility. And light wave technology, it is the only technological route for achieving this goal. So light wave technology, it is a cost effective way. When I say cost effective, only cost is not the factor. Advantages are also the factor. So cost effective way to move huge amount of information. The optical fiber, it has a huge bandwidth, huge capacity. So all sort of information they can put over the optical fiber. All voice, video and data, we also call it as the ISDN, integrated services digital technology or digital networks. So all with it happens only with the optical fiber. It transfer, it's a very quick way of processing or movement because it involves the photons, and we know the photons they travel fastest. And then of course reliable. The fiber, the system has to be very reliable. So this is the light wave technology and the requirement or need of the technology. And then of course why we need the optical transmission. The other parties, we have radio wave communication, we have the microwave communication. They are well established technology, and they in these technology they are both point to point link as well as the wireless technology. But what is the need? So then the point arises, it is the capacity. We need more and more capacity. Our communication need day by day they are increasing. Earlier we were interested only in the voice. Now we want the voice, we want the information, we want the internet, we want the multimedia also. So everything is to be put over the communication system. To reach to the society, the only way is the communication system. So as a result, the capacity of the system has to be upgraded. So we need more and more capacity for the system, and a result to fulfill this need, there is a technical revolution in the communication industry to explore for large capacity, huge, high quality and economical system. Not only for at the national level, but at the global level. Today, the world is global village. So all the information has to be shared at the international level, and to fulfill those requirements, different developments have to be taken place. So we have radio and wave and terrestrial microwave systems. They were developed in the 19th century, and then radio wave and microwave system they are fulfilling the need of the society in the past, but they have reached their capacity. The bandwidth of the system is not very high, so you cannot add more to these systems. So as a result, one have to go for the alternative. And these radio wave and microwave, they cannot go to long distances. They cannot fulfill the global requirement. They cannot be at the international level because of the long length limitations. So as a result, one have to look for the system to fulfill the global need. One go for the satellite communication. So satellite communication, it can provide at best only a temporary relief to ever increasing global demand. The satellite, in the satellite communication, we have the geostationary satellites, and from the satellite we can have a uplink and we can have a downlink, and it can go all over the globe. So as a result, satellite communication is the only media, but it has the many limitations. The important point is extremely high initial cost of launching. So launching a satellite involves huge expenses. Every country cannot afford to launching number of satellites. So it's a very expensive option. The geometry of suitable orbit. The satellite have to be put in certain orbit in the space. Already you must have learned on in the newspaper or in the media that there is a lot of traffic in the space also. Number of satellites have been launched. So as a result, it's an international affair. One have to go to the international agency for providing the suitable orbit, and one have to pay for that also. So again, it adds to the cost. Then available microwave frequency allocation. We have already discussed the radio and microwave. They have reached their capacity. And for satellite communication, at least I need two frequencies, one for uplink, one for downlink. So from where it will come? So as a result, this is again a limitation, the allocation of microwave frequency for satellites. And then if needed, repair is nearly impossible. It is very difficult to repair a satellite. Only you can drag the satellite and you can orient it to fall somewhere in the ocean if it is faulty one. So as a result, it's a very expensive affair. The system is not economical. So as a result, we have to look for another system. We have to look for the next option. And all our communication, we know it is based on the electromagnetic waves or wave from the electromagnetic spectrum. So we have already covered radio waves. We have gone to the microwave frequency. Now next option is, if you want to achieve more, you have to climb up the ladder. So the next option in the electromagnetic spectrum is the optical frequency. So as a result, the optical communication system, they are working on the optical frequency and they have achieved a great attention for development. So optical communication is the only option to fulfill the communication needs of the present scenario. So this is the electromagnetic spectrum where you can see we have already covered the radio wave, long wave radios, short wave radios and microwave. Now the next part is the optical frequency. The optical frequency, if you look at these frequency part, the radio wave they work in the kilohertz frequency, microwave they work in the area of maybe 1 to 10 gigahertz, and then the optical frequency they work in the area of terahertz. They have the terahertz frequency, 10 to the power 14 to 15 hertz. So very high frequencies. So if you go further, look at the requirement, the potential of optical transmission. The communication need can only be fulfilled by the high frequency optical wave. The information carrying capacity of any system is proportional to bandwidth. So if you want more capacity, I need more bandwidth. And this is best quoted by Shannon-Hartley theorem, which mentions capacity is equal to bandwidth into log 1 plus signal to noise ratio, SNR. So you can improve the signal to noise ratio of the system, but there is a limitation. If there is improvement, then it is in the log term. So contribution is very small. On the other hand, any change in bandwidth is directly proportional to the capacity. So the better is go for the higher bandwidth. So further, so wider the bandwidth, greater is the information capacity of the system. And theoretically, we know the bandwidth of the system is 10% of the carrier frequency in general. So higher the frequency, more will be the bandwidth. You can have a simple comparison. So if you have a signal carrier working at radio system, say 10 megahertz, the bandwidth 10% of it will be 10 megahertz. For microwave system, around 6 gigahertz central bandwidth, so maybe 0.6 gigahertz, 1000 times more, maybe 100 times more than the radio wave system. Light wave system, they are working at 10 to the power 6 gigahertz. So if you find the bandwidth, it is around 10 to the power 5 gigahertz. So it is around 10 to the power 4 times more than the radio and microwave system, or 10 to the power 5 times. A system lightweight, it has excessive bandwidth, more than 100,000 times more than the microwave frequencies. So it is a huge bandwidth. And it meets the today's communication need or that of the foreseeable future. It's a huge bandwidth and it will fulfill the need of the communication industry maybe for coming 50 to 60 years. There may not be need to go to the next in the spectrum. It has that type of sort of potential. Sometimes we also call the optical communication and infinite bandwidth. It's a very huge bandwidth. So as a result, this communication system as a light, it has a great deal of intention. Lot of research, lot of efforts are required to develop the system. So, but there are the difficulties. Optical communication is not just like radio and microwave communication. It has a difficulty for transmission, difficulty for transportation, for propagation, and it is all because the transmission of light wave in the atmosphere is impractical. It is because of the high attenuation and absorption of ultra high light frequencies. Optical frequency, they undergo large attenuation or absorption by different particles. Attenuation is through the diffraction or through the scattering. And below the diffraction is prominent if the wavelength of light matches the obstacle. The optical frequency in the range of micron, 1 micron or 1.3 micron or 1.5 micron or nanometer, and the particulate in the atmosphere, they are also of the same size. As a result, there is a huge or large amount of diffraction, and then we have the scattering, Rayleigh scattering. So larger the wavelength, more is the lesser is the Rayleigh scattering. So all these aspects, again, these optical frequencies, they are absorbed by water vapors, oxygen and air particulate. So as a result, the only practical type of optical communication is the point-to-point link. We need the light guides or fiber guides, and this fiber guide is nothing but it is an optical fiber. So it is a point-to-point link. Just as an electrical wire or metallic conductor, I need an optical fiber for communication. So optical fiber, it is a strand of glass or plastic material with special optical properties which enable light to travel a long distance down its length. So it is made from a transparent material, and we know for light propagation the media has to be transparent. So it is either the transparent material or either plastics or the glass. So depending upon the quality of the communication, depending upon the quality of the fiber, it can be made from plastic or it may for best performance it is made from the glass. So we have the optical fiber. So there was a need of optical fibers, and for communication we need optical fiber with minimum attenuation and very small dispersion. These are two communication parameters, attenuation and dispersion. Dispersion can be related to broadening of the pulse. So these two aspects have to be fulfilled, and another requirement is the powerful and intense optical sources. I need a very powerful source. My communication can be long distance if my source is powerful. I need more power. In fact, optical communication is not a new technology. It's a very old technology. The communication, or maybe from the origin of this the human mankind. We use the optical signal. Fire was used to communicate. Still, it is one of the mode of communication in the remote areas, but it cannot be long distance. It was only the shorter distances. So as a result, we need very powerful and intense optical source for optical communication. So it all happened with the development of laser. Invention of laser in 1960, and then development of low loss optical fiber in 1970. So laser, basically with the development of laser, it brought up a revolution in the optical communication industry, and ultimately today we have the optical fiber communication which fulfill all the need of the communication industry. So this is the development of lasers and optical waveguide was an edge toward making the dream of carrying huge amount of information a reality. So it is all with the laser and the optical fiber. But the optical fiber which were available at the time of invention of laser, they were very lossy. The losses were not very low. Because if you are going for an alternate communication media, the losses should be comparable to the existing media. We were using copper or coaxial cables as the communication media. The losses were around 20 dB per kilometer. So if you are going for replacement of these type of conductor with the optical fiber, you have to reduce the losses to low level, at least comparable level. That was the idea that lead to development of communication. So the optical fiber, basically, you know, the Moga man, father of fiber optics, it was Dr. N.S. Kapani who worked a lot on the optical fiber, but his intention was not to develop the optical fiber for communication application. He worked for all these developments in the area of the field of medicine. So flexible endoscope. So endoscopy is basically from the optical fiber. So he was not, you can say his efforts were not recognized because the communication was the only the motto for optical fiber communication. So this is a fiber optics timeline. If you look for these developments, we see the light transmission through bundle of fiber, flexible fiber scope used in the medical field, and ultimately first fiber optic endoscope tested on the patient. This was the contribution by Dr. N.S. Kapani. So we have the endoscope and which works on the optical fiber. But requirement was not the long distance. Endoscopes, they are hardly 1 meter in length. So attenuation was not the big criteria. Then invention of laser in 1960. P. Mayman developed the first laser, and Charles Cow, he proposed that cladded fiber cable with lower losses, they can be used as a communication medium, because in the communication industry the problem was of losses and broadband. So if he proposed that if we can reduce the losses in the optical fiber, the same cladded fiber can be used as a communication media, and the idea picked up by the Corning, and they come out with a optical fiber with losses below 20 dB per kilometer, which is comparable to the coaxial cable. So as a result, the optical fiber communication fibers were available, lasers were available, and then the field it gained a lot of importance. And second, in 72, for communication need, I need a light source which can be modulated. The lasers or semi-critical lasers which were available in 60s, they were having fixed output. We are not able to change, we are not able to modulate them. So it was a semi-conductor diode laser which is based on the injection current. So they are also called injection laser diodes, ILDs. So they are based on the input current. So I can modulate this input current and I can get the modulation. So they were developed at a later stage, and it was in 1977 that first Bird's fiber optic telecom link was established. That was tested. It was tested by GT&E in Los Angeles, and at the same time by AT&T in Chicago. They sent live telephone signal through fiber optics. The system they developed at 850 nanometer. This is the far end of the optical spectrum. And then they used the multimode fibers. The data rate was around 6 Mbps and 9 kilometer repeated spacing. Repeated spacing is the distance after which we have to repeat the signal. We have to amplify the signal. So for copper system, after every 3 kilometer we have to put the repeater. But in optical fiber, the first link was established with the 9 kilometer. So it reduces the number of repeaters to 1/3. So reduces the cost also. That's why I said that it is a cost-effective technology. So today we can have an optical communication link with repeater spacing more than 100 kilometers, depending on the data rate. It can be 150 kilometers. So this the first of fiber optic link was established. Then in 80s there was the second. This is the first generation system. We have the second generation system where the communication wavelength, propagation wavelength is shifted from 850 nanometer to 1310 nanometer. So it is all to reducing the attenuation. If we work at 850 nanometer, attenuation is more, maybe around 4 dB per kilometer. But at 1310 nanometer, the lossy reduces to 0.5 dB per kilometer. Again, instead of the multimode fiber, another issue in the communication is the broadening of the pulse or dispersion of the pulse. In the multimode fiber, there is the dispersion, we call it as the intermodal dispersion. Number of modes travel in the optical fiber, that lead to broadening. So as a result, the technology shifted to single mode fiber. If we have a single mode, there is no broadening, there is no intermodal broadening. So as a result, multi-mode fiber, they were placed with the single mode fiber and the lossy reduced to 0.5 dB per kilometer. And at the repeated spacing, obviously we have to amplify the signal. Our signal is optical signal. So in order to amplifiers were not available at that time. So we have to convert the optical signal to electrical signal, amplify it, and again convert electrical to optical signal. So this was the bottleneck in the communication system. Conversion from optical to electrical, electrical to optical, it is not always 100% efficient. So losses may occur during this conversion. So as a result, the amplification was the problem at 1310 nanometer. So in the third generation system, the wavelength, propagation wavelength shifted to 1550 nanometer. Again, we have lower losses. From 0.5 dB, the losses reduces to 0.2 dB per kilometer. Again, one use the single mode fiber, and then it gives the evolution of EDFA, erbium doped fiber amplifier. It is an optical amplifier. So it will amplify the signal in the optical regime. There is no need to convert from optical to electrical. So that added a third another dimension in the optical communication, and now through optical system we are able to send the signal at very high data rate, maybe 5 GB Gbps, 10 Gbps, now 40 Gbps or 100 Gbps system, they are very common. 40 Gbps system, they are very common. 100 Gbps system, they are also under development. So this is the scenario for these developments. Then in 90s, Bell Labs, they send 10 billion bits through 20,000 kilometers of fiber using solitone systems, solitary waves. Solitary waves are the non-destructive waves. They will not disperse, non-dispersive pulses. They can cover long distance, and then again with the help of WDM technology. So the 90s period that lead to development of the WDM technology, wavelength division multiplexing. I can send number of wavelengths over the same fiber, provided they should be different wavelengths, because you know the different wavelengths, they travel different distance. So WDM technology, and then in 2000 or 21st century, even the company they are working to send trillion bits per second, terabits of the data through single optical fiber, and that lead to development of all optical networks. So we need now all the optical components. If you look at the architecture of a computer, even in its initial development, we have the CPU, we have the memory system, we have input-output devices. Today, it is the same system. The only efforts are to increase the speed of the CPU, to have more and more fast memories, to attach more and more input-output devices. So all efforts are to enhance the speed. Similarly, in the optical fiber communication, system has matured enough. The efforts are to enhance more and more data communication, data transport. So earlier, initially it works at Mbps, it goes to Gbps. Now the next approach is for the terabit system, and for that part, we need all optical network. Why we are not achieved to terabits per second? It is all because of electronics. Electronics is not able to cope up with that speed. So we need to remove all the electronic components from the optical networks. Everything has to be on the optical network or optical communication. There should not be any transformation from optical to electrical, electrical to optical. Then only these are the latest developments. So the Nobel Prize in Physics 2009, it goes to optical fiber communication development. Charles Cow, he was awarded Nobel Prize for groundbreaking achievements concerning the transmission of light in fiber for optical communication. So it was the recent Nobel Prize in Physics 2009. So a fiber optic link, we know that in any communication system, I need a transmitter where we have to modulate the information. So it comprises of a transmitter which has driver and the light source. This light source is a optical source. So we have the same electrical signal. Now this electrical signal will be converted to the optical signal. So it becomes an optical communication, and it converts electrical signal to light signal. A driver modifies the information into a suitable form, or what we call as the modulation. So source is either LED or injection laser diode, whose output is modulated. So we have the modulated optical signal for launching over the optical fiber. Similarly, we have the receiver component. At the receiver component, we receive the optical signal. This optical signal is converted to electrical signal by a optical detector, which is either a pin diode or an APD. So electrical signal is demodulated to separate out the information, and finally this information is delivered at the destination. So this is a part of the communication, and in between we have the optical fiber as a medium for carrying the light. So our optical communication or optical system, it comprises basically of three components. One is the optical source, another is the optical detector, and then the optical fiber. So optical fiber or fiber optics technology, it is concerned with the development, with the research in all these three areas. We have to work in enhancing the quality of the optical fiber. We have to work in getting better and better light sources, better and better detectors, which can work at very, very low power. So all this is the optical communication system. So these are the components, these are the optical fiber system devices. So transmitter, which is either a laser diode or an ILD or an LED. So it can be a LED or it can be a ILD depending on the requirement. Similarly, we need optical fiber as a communication media. So when this optical fiber is to be used, fiber has to be converted to a cable. When I am saying optical fiber, it is a simple fiber with core and cladding. It is a glass material. If it has to be used in the field, so it has to be provided a mechanical strength. It has to be made more and more mechanically strong. So as a result, the optical fiber is to be converted to an optical fiber cable. So it is the cable which is used for the practical application or in the field. Then of course the receiver. So receiver is the ultimate, at the end where the signal is received and it is converted to the suitable form for delivering to the users. So mostly we use pin, which is a pin diode. These are the reverse bias detector. It is a P, I and N region. Pin detector, and we have the APDs, avalanche photodiodes. So they work at different power. APDs, they can work even at a very, very low power at the order of nanowatt. Pin, they can work at the order of microwatt. So they have different sensitivity. So depending upon the requirement, we have any of these combinations. So, and the backbone of an OFC system is the optical fiber. The most of the discussion which act on of our this course will be on the optical fiber. It acts as a transmission channel for carrying light beam loaded with the information. All the information you can reach from one place to another place if you have a very good means of transportation. So optical fiber is basically transportation media. It should be high quality fiber. It should be with minimum distortion or minimum losses. So we have the optical fibers. So optical fiber, it acts as a transmission media. It transmits data as light pulses. So it converts the electrical pulses to light pulses. These light pulses, they travel in the optical fiber, and ultimately at the receiver side, optical signal is again converted to the electrical pulse. Because our appliances, they are responsive to electrical signals. Our telephone instrument, our mobile, they need electrical signal to work, to respond. So ultimately it has to be converted to a electrical signal in the present scenario. Maybe in future our instrument may be responsible to optical signal. Then there is no need to convert from optical to electrical. Still systems are under development in this area. And for transmission of signal, you see the light propagate by beam of total internal reflection. The signal travel in the optical fiber by total internal reflection. So this is must for propagation. So our optical fiber should fulfill the requirement of total internal reflection. So our fiber, the light rays, they enter in the optical fiber at different points, they undergo total internal reflection. So this condition has to be fulfilled. So this is the structure of optical fiber. If you look, the fiber is a dielectric core made from doped silica of high refractive index. It is surrounded by a lower refractive index cladding. So we have core and we have the cladding. It is required to fulfill the requirement of total internal reflection. The core is of high refractive index and cladding is of low refractive index, because the total internal reflection only takes place if light goes from denser to rarer medium, and the total internal reflection is at core cladding interface. So light should enter from the core to the cladding, and at the surface it undergo total internal reflection. So for total internal reflection, core and cladding should be of different refractive index, and the refractive index of cladding should be lower than the core. And there are different configuration. We have the core and cladding, we have the step index fiber, we have the gradient index fiber, which differ in the by means of the refractive index profile. So whether it is a homogeneous refractive index profile or it is an inhomogeneous refractive index profile, it depends. It classifies between step index and gradient index fiber. We will discuss these in the more detail in the next lectures. Then fiber can be a single mode fiber or it can be a multi-mode fiber. It can support number of modes or it can support a single mode. Accordingly, they have different dimensions also. The multi-mode fiber are larger in the diameter, maybe from 50 micron or 62.5 micron. These are the standard for these fibers. Similarly, single mode fiber, if you want to allow only the single mode propagation, we have to reduce the diameter. We have to reduce the aperture. So as a result, single mode fiber, they are either from 5 to 10 micron. And this is a necessary condition for total internal reflection. N1 should be more than N2. These are transmission losses in the optical fiber, fiber glass. So you see the development of optical fiber is started in 1966, and within a small span of time, the losses has been reduced from say 100 dB to 0.1 dB. So in a very small span of 10 to 15 years, the losses have been reduced. So initially the losses were around 20 dB per kilometer. Then it reduced to 5 dB per kilometer, and today we have optical fiber with losses around 0.2 dB per kilometer. This is the lowest theoretical limits. So practically we have the optical fiber with 0.2 dB per kilometer. The system, they are working at 1550 nanometer. So this is a very fast development in the optical development of optical fibers. This is the communication channel capacity of the system. If you look, I have already given the comparison. If you look at the copper cable, the bandwidth is around 10 kilohertz, and I can add around 2000 voice channels on the system. If I want more channels, more voice channels, I need more cables. So from single copper cable, you have to go for the multiple copper cable, different pairs. Similarly, for coaxial cable, they work around 10 megahertz. So around 1300 telephones can be put over the single coaxial cable. On the other hand, if you look at her optical fiber cable, it works at around 40 terahertz. So more than 3 lakhs telephones can be put over the single optical fiber. More than 90,000 video signals can be put over the optical fiber. This is the potential of the optical fiber. So it can handle all the needs, whether it is a need for communication of the voice or data or multimedia. So it provides a broadband communication system which fulfill all the requirement of the communication society. So two major communication I already talked. One is the attenuation. In any communication system, one is the attenuation, which is the signal loss over the distance. So light pulses lose their energy as they travel down. So it put the distance limits. How long I can reach. So I need minimum lower the attenuation, more is the distance to be covered. So we want minimum attenuation to be as small as possible. Second is the dispersion. Dispersion is the broadening of pulse. If my pulse is broadening, I cannot operate the system at very high data rate. So narrow the pulse, more will be the data rate. Mbps per second. It means number of pulses on a 1 second slot. So it increases from kbps, mbps, our gbps or terabits per second. So when I'm talking about the terabits pulses, my terabits of the data, my pulses are of the order of femtosecond bit. So very fast pulses are required for those requirements. So these are the two communication issues. So it puts the data rate limitation on the network. So there should be minimum or least broadening of the pulse. And we know that light property dispersion is an inherent property of light. We cannot avoid, but we need the optical fiber which give the minimum dispersion. So fiber attenuation, I mentioned this is the characteristic curve for the silica fiber, and how the system, how the losses reduces from 850 nanometer to 1310 nanometer to 1550 nanometer. The attenuation reduces from 4 dB per kilometer to 0.2 dB per kilometer. So this is the attenuation curve. Similarly, the fiber dispersion. We developed the fiber. The fiber has been developed as a multi-mode step index fiber. Multi-mode fibers. We have the multi-mode gradient index fiber. We have the single mode step index fiber. In all these categories, the dispersion reduces. In multi-mode fiber, there is a large dispersion, large broadening. With the gradient index fiber, small broadening. In the single mode fiber, the dispersion is minimum. So dispersion is minimum in the single mode fiber. So for high data rate, we use the single mode fiber. And we have a number of fiber, like they differ. We have the step index profile, we have a gradient index profile, just to overcome the dispersion, to minimize the dispersion. So as a result, these parameter attenuation and dispersion, they decide about the wavelength of operation, because these are the optical windows. So the first window was 850 nanometer, where the attenuation is large, maybe around 4 dB per kilometer. So then we have the second window, 1310 nanometer window. Now we have the 1550 nanometer window. Here the losses are very small. So mostly the optical communication work on these windows. Earlier, these 1310 and 1550, they are very important windows, and most of the communication system now work at these windows. But 850 nanometer, now it has also gained importance because of the networking, because of the local area networking. We can use this 850 nanometer, or because of the now the attraction for the last mile. We have at the end, we can use the 850 nanometer, because here the distance is not important. Importance is the connectivity. So we can also use the 850 nanometer for local area networking. So then we have optical sources. I mentioned we can have the LEDs. So a lot of efforts are also required. We need the parallel development in optical sources. So these are mostly made from the alloy semiconductor. So maybe gallium, aluminium, arsenic. The first device is made from gallium arsenide, which work at 850 nanometer. There can be binary alloys, there can be tertiary alloys, there can be quaternary alloys. So accordingly, we need for 850, for 1310, or for 1550. We have to see how we can use different alloys for better and better property of an optical source. Because all these attenuation, it depends on how much power is available. I need a powerful source. Dispersion, it depends what is the spectral width of the source. So lesser the spectral width, lesser is the dispersion. So I need a optical source with very small spectral line width. So as a result, one have to different parts. So LEDs, they are low cost and easy to use. Similarly, they use for the multimode fiber because their line width is more. They have spectral width of the order of 30 to 40 nanometer. So as a result, we need special type of LEDs like edge emitting LEDs. Most of our LEDs, conventional LEDs, they are the surface emitters. The spectrum is very broad, but for optical communication, we know the optical fiber is of around 10 micron diameter. I need a very narrow or very narrow source with very small line width. So you can use a special type of LEDs for the single mode fiber. But ultimate solution is the laser diode. Laser diode, mostly they are the quaternary alloys and different combinations are possible. I can have a laser diode in all the three windows, but they provide very high power output. Laser output maybe 100 times more than the LEDs. In the LEDs, the power is hardly in the order of microbarts. Whereas for the laser, it can go to even milliwatt or even watt or even very high power depending on the requirement. But for mostly for the communication, we can have the milliwatt laser diodes, because more power is also not desirable in optical fiber communication. That lead to different type of impairments. So they can work at the high speed. They are very expensive also. Developing or laser, it is a high cost component as compared to LEDs, because it needs very special power supply and circuitry, special type of controls. So one have to decide whether to use the LED or to use the laser for the quality of the services. Similarly, we have the optical detector. Optical detector, it can be a pin diode. It is the positive, intrinsic, and n-type material. So again, they can be made from silicon, germanium, or the alloys. So they cover all the three windows. They are low cost component. Like our LEDs, I can have a pin diode. On the other hand, I have a avalanche photodiode, APDs. They will be only made from the alloy semiconductors. They are available in all the windows. Of course, our detectors are very broad. The detector is cover a large span of the communication windows. They have a high sensitivity. They can operate at very low power level, maybe of the order of nanowatts, but they are expensive. So one have to decide the best combination is your laser and APDs or single mode fiber, or we can have a low cost component LED and pin diode. So it depends upon the service provider, or it depends upon the quality, what type of quality is required for a system. So then I will cover to the advantage of optical fiber. So when I cover the advantage, I will compare the optical fiber with a metallic conductor, copper cable or aluminum cable. So one is the wide bandwidth. They have the extremely high information carrying capacity, bandwidth of the order of terahertz. So number of channels, all the integrated services or broadband services, they are only possible with the optical fiber. High data rate systems are possible. 2.5 Gbps, 5 Gbps, 10 Gbps, 40 Gbps, 100 Gbps system. They are already there for the commercial activities or for commercial services. Low loss. So information, large distance, information can be sent over large distance. Very low attenuation, 0.2 dB per kilometer. A copper cable, it has attenuation of the order of 10 dB per kilometer. So 100 times less distance, less loss as compared to copper, means 100 times more distance is possible. So repeater spacing more than 100 km, whereas for copper cable the repeater spacing is around 3 km. Interference free, so they are immune to electromagnetic interference, no crosstalk, can be used in harass and noisy environment. There are lot of EMI are there, but optical signals they are not affected by EMI. High security, no radiation. The signal travel in core only. No energy is irradiated. Whereas in copper and other, so difficult to tap. So the stealing of signal is not possible in this case. It is very difficult to optical power. If one have to tap the optical signal, he has to break the optical fiber. He have to join core to core. Whereas in copper cable, if you just twist the two wires, you will get the signal. But whenever you have to use you have to tap the optical signal, you have to at least break the fiber and join the core to core. So doing the breakage, one will get the signal information. So they are very attractive for defense, intelligence, and bank network, where the security is a very important criteria. Then compact and lightweight cable. The optical fiber, they are very small in size. The fiber is thinner than the human hair, 10 micron. So ultimate signal will travel in the 10 micron diameter. They can replace 1000 pair copper cable. A single optical fiber can replace a 1000 pair copper cable. Fiber weighs 28 gram per kilometer. It's very lightweight cable, considerably lighter than a copper. Then lightweight cable also. So even the cabling of layer, it is all with the polymers, and the optical fiber is very light as compared to the copper cable. So they are very portable. As a result, they save a lot of transport and expensive. Then environmental or immunity. So greater safety. Optical fiber, it is a dielectric. No current, no short circuit, no fear of fire. So as a result, they can be very safely used in hazardous environment. Very attractive for oil and petrochemical industries. There the short circuit is a problem, spark is a problem, that can lead to lot of losses. So it is very attractive for these applications, not prone to lightning. Then by temperature range, optical fiber can work at very high temperature. The melting point of glass is 1410 degrees centigrade. It means they can work very easily up to 1000 degree or 1200 degrees centigrade. So in environment like our nuclear reactors, where the temperature is very high, the carrying of signal or controls is possible with the optical fiber. So they are very attractive for the high temperature system. Similarly for low temperature, of course. Then long life. Optical fiber, they have very long life, more than 30 years. The fiber which were installed or commissioned in 1977, still they are working at their full potential. So it means their lifespan is more than 30 years. For copper, how much is the lifespan? A copper cable has to be replaced after how many years? Any idea?
Around 10 years.
Yeah, very rightly. A copper cable has to be replaced after every 10 years. The service provider may or may not do, but as per standard, a copper cable has to be replaced after every 10 years. Whereas optical fiber communication cable, it can work up to 40 years. So that leads to what I call the cost-effective system. The initial cost of optical fiber may be more than copper, but it has long life. So ultimately, it comes to be cheaper as compared to optical fiber. On the other hand, it has many advantages over the optical copper. So these are all the benefits. And then abundant raw material. Optical fiber is made from silica, sand. Huge amount of sand is available at our sea beaches. Whereas it is not a scarce resource as compared to copper. So this is another advantage for the optical fiber. So all these are the advantages of optical fiber as compared to copper. But then it has some disadvantages also. We should not always talk about the advantages. Disadvantage: the optical fiber are relatively expensive. Initially, they are more expensive than the copper, but life is more. Then connectors are very expensive because due to high degree of precision. In a copper, we can the cable is of larger diameter. The optical fiber, the connector has to be put over the core and cladding is 125 micron. So as a result, I need a connector of that much size. So it adds to the cost. Normal machining will not work with these connectors. We need special type of machining, maybe with the laser based technology, laser machining. So that adds to the cost. Similarly, connector installation is time consuming and highly skilled operation is required. You have to put the connector over the micron size. It needs a lot of practice. It needs time, and we will see to the connector. Each connector is made of almost 3 parts. You have to put the connector part by part over the optical fiber. So that needs a lot of practice for and skilled operation. Then jointing of the fiber, it requires expensive equipment and skilled operation. It is not just like copper. You just twist the 2 cables, you will get the joint. But here you have to make a joint in the glass. And for glass, I mentioned you have to go at the melting point of the glass. This is just like a welding. So you need very source which can give you huge amount of heat. So especially we need the arc discharge or fusion sparks. So that adds to the cost. So special type of units are required, splicing units, splicing machines, and then accuracy at the precision level. Alignment of the optical fiber is very important. If 2 cores are not aligned, there will be a huge lot of signal. So alignment has to be at a level less than micron size. Then connector and joints are relatively lossy as compared to copper. When they are highly precision required, even a small loss add to the lead to a huge loss. Because in the optical fiber, the power is already limited. That's why we go for the different budgets. I cannot send large power in the single mode fiber. That will lead to non-linear effects, which we want to avoid. So, as a result, they are difficult to tap in and out. I mentioned it as an advantage. But nowadays, because of the networking requirement, we have to tap the signal. And it is an optical signal. Signal has to be tapped in the optical domain. So as a result, we need couplers. So couplers, they are to split the signal or to combine the signal because of present requirement. So they also add to the cost, expensive coupler. And then of course, relatively careful handling is required. Optical fiber is made from glass, and whenever we talk about the glass, we know that we have to handle it more carefully as compared to other metallic part. So these are different disadvantages which lies with the optical fibers. Then we have the OFC systems. They are initially installed for 1310 nanometers. At this wavelength, the loss, there is a low loss, but not minimum loss. This is a low loss, 0.5 dB per kilometer, but not minimum. Minimum pulse broadening, but dispersion is minimum at 1310. So these 2 parameters, attenuation and dispersion. I say both should be minimum, but they are not meeting at the same wavelength. At 1310, attenuation is low, dispersion is minimum. At 1550, attenuation is minimum, dispersion is more. So one have to, both the channels, they have their own importance. 1310 is important for high data rate. 1515 is important for long distance communication because attenuation is lowest. At 1310, dispersion is lowest. Then regeneration of signal at 1310, it is the conversion of optical to electrical. So electronic amplifiers they are used because there is no promising optical amplifier at 1310. EDFA, it is only working at 1550 nanometer. It cannot be used for 1310 because no amplifier is performing as good as EDFA at 1550 nanometer. So it is mostly one use the electronic amplifier at 1310. Then we have the future system, they are based on the 1550 nanometer. In fact, the second generation system was 1310. Naturally, they were installed first before the 1550 nanometer system. So here at 1515 wavelength, silica has lowest loss, but increased dispersion. So loss is lowest, it is the one parameter, but dispersion increases. So it has benefit of long distance communication, but not at high data rate. So this was a limitation. But it is not in science or in engineering. Whenever we have any problem, if we know the problem, we have the solution. We can design an optical fiber which we call as the dispersion shifted fiber. Dispersion shifted fiber, it is there at with lowest loss and lowest dispersion. Only point is you can shift the dispersion minima from 1310 to 1550. But then you have to play with the configuration of the optical fiber. This fiber may not be similar to your conventional fiber like core and cladding. They may have more cladding, there may be segmented core, and it may be of different type of profile, but they are there. So dispersion shifted fiber DSF with lowest loss and negligible dispersion, they are possible, but they are not used conventionally because they are more expensive as compared to conventional fiber. Manufacturing will be more expensive, and wave guiding will also be more critical. Then erbium doped fiber amplifier EDF, it works at 1550 nanometer window with lowest loss. It has a flat gain. So for performance of system it depends on the bandwidth. Flat gain. It means it can amplify all the signal in that window. So EDFA, it has a wide band, enormous potential, wide band, flat gain. So as a result, I can amplify all the signals within that bandwidth. So EDFA, it is again a fiber, erbium doped fiber. The fiber is doped with the erbium, so it acts as a laser. Laser is a light amplifier. So it accepts the optical signal at 1550 nanometer, and it comes out with a optical signal 1550 nanometer. So it amplifies the carrier. So if carrier is amplified, signal will automatically be amplified. So erbium doped fiber amplifier is a solution for the optical amplification. So the next requirement is optical communication is to how to enhance the network capacity option. So we can have an optical fiber which uses the optical amplifier 1550 nanometer window, minimum loss, minimum dispersion. But how to tackle different requirements, different users? So as a result, we have to enhance. If we have to need very fast traffic, if we have to tackle large traffic, either the road has to be very good quality, or now there is a concept of laning, 4 laning, 6 laning, 8 laning. Similarly, here we can also have that concept. It is all the traffic, so we can have more fiber, because a fiber has certain limitations. The dispersion cannot be reduced to 0. So if you want to tackle high data rate, you can work on a fiber with a specific data rate, and you can add more fiber. What we call the space division multiplexing. We have to go for the multiplexing. Similarly, in that case, I need the fiber, each fiber work at the low data rate, but I need more fibers. Adding more fiber means adding more cost. So it is expensive in engineering and limited to different parts. I need more ducts for optical fiber. Another approach is time division multiplexing. That is usually used. So we put all the signal in the time domain on the first user, second user, third user. We divide it into different framing system. So TDM frame. So if you want faster and faster data rate, your timing pulse has to be as narrow as possible. It means very faster electronics. So higher bit rate on same fiber, but you need very narrow pulses. So very fast electronics. It means more cost. May not be caught up with the pulses of the order of 10 to the power of minus 15 nanosecond, minus 15 second, or femtosecond pulses you have to generate. So that is a limitation. Then we have the another option, WDM technique. Same fiber, same bit rate, but more wavelengths. So you can have fiber but number of channels. This is just like the national highways. We have more systems. More vehicle can run on the same road. Similar case, I can send number of wavelengths. I cannot send number of currents on the same copper because they will generate the spark. But I can send number of wavelengths on the same fiber because they will follow different path. Each wavelength will follow different path. So wavelength has to be different. So that is a unique feature of optical fiber communication. So WDM is possible. It is similar to frequency division multiplexing. So all of these systems, coincidence of low loss window and wide band EDF. So that gives the possibility of WDM communication. I can amplify all the wavelengths simultaneously with the EDF because it has a flat gain. All the wavelengths should fall within the flat gain of EDFA and they will be amplified simultaneously. So that is capable of carrying enormous rate of information, very high data rate. So WDM concept. Only I need the number of sources, number of wavelengths has to be generated, but same single fiber. So only I need a multiplexer. This is a wavelength with a multiplexer. You can have number of wavelengths, or these can be different type of information. One wavelength may carry the voice, other wavelength carry the multimedia, another wavelength carry the data or information. They can be multiplexed with a multiplexer and they can be put over the single fiber. So this is a WDM technique. We will discuss it at the later stage in detail. So it will be put over the same fiber, and in between we need the amplifier, we need the another engineering system to transport the data, and at the end again I need a wavelength division demultiplex. I have to separate different wavelengths. So these wavelengths they can be provided to different users. So this is the technology which is only possible in the OS. So as a result, it is a very high power WDM network. The example system has already been developed and put in use. Even in Chandigarh, they are using these telecommunication on the DWDM system. We have the regional northern telecommunication link NTR at Chandigarh, which is covering all the system on the DWDM. It is taking all the information. So terabits of data are possible with 55 wavelengths. Similarly, 2.6 terabits up to 120 kilometer repeater spacing at 132 wavelengths. So I mentioned there is a limitation. You cannot put high data rate over the optical fiber because of the dispersion problem. But your fiber can work at the lower data rate but more wavelengths. Suppose I want a 100 Gbps system. It is better to have a system working at 2.5 Gbps and 40 wavelengths. I will get 100 Gbps. Or there can be 10 Gbps data rate and 10 wavelengths. But at 10 Gbps, we have a lot of problems. At 2.5 Gbps, that is the ideal data rate. That is the outcome of the search. So then these are the bandwidth revolutionary. I mentioned optical fibers, they are deployed at a rate of 2000 miles over the globe. Huge requirement, huge deployment. And then of course it is only possible with the high data rate, with the EDFA, WDM, then high speed optoelectronics component and advanced fibers with lowest loss. If you look at the comparison, the high data rate is possible with the TDM. That is a conventional technique. But TDM it started maybe from 80s and it reached to high data rate. Whereas OFC WDM is started in around 80s, and you see business span even in 90s it crossed the conventional TDM. It can provide high data rate. Where the TDM it took long to achieve this part. Now it has crossed the TDM. So number of wavelengths around 80 wavelengths at 40 Gbps. It can give huge terabits of the data. So terabits is only possible with the WDM, not with the TDM. Will not lead to that type of developments. Only gigabits one can think with the TDM, because the so narrow passages are not possible. Another approach, bands in the light spectrum. If you look at the light spectrum, approximate attenuation, you see we are using these two band conventional bands, but we can use the another windows, maybe S band, like this region can be utilized. Similarly, higher regions can be utilized for different applications. Similarly, this region can be utilized where the distance involved is more, not more. Here only the loss is more, but I can use this window for the shorter distance, for the medium haul link. So bandwidth is available. It is not that bandwidth is not there. It is available, but maybe for the shorter distance. It is not that there is always a long distance requirement. We have medium requirement, we have the short distance requirement, we have a local area networking requirement. But they are only possible at different wavelengths. So we can use these windows also. So optical communication, it provides a express way. It is a national highway, so where parallel traffic can move. So here number of wavelengths can move. So different companies they are providing all the limits. So lightweight communication system deploying DWDM, EDFA and solid-tone pulses. They can provide zero loss and infinite bandwidth. It is a huge bandwidth provided by optical fiber, and it can provide a network capable of handling almost all information needs of the society. So they can, this is the next step. The next step is the fiber to the premises, fiber to the home. Presently optical fiber they are used, maybe all the central exchanges they are connected by the optical fiber. Central exchanges to trunk line they are connected by the optical fiber. It is not at the last mile, what we call the local loop. So now it is a requirement. Fiber to the home, fiber to the premises, fiber to the any place. That is a present requirement in the optical fiber. Fiber to the home or premises. Like we can use the number of wavelengths for different applications. 4090, 1310, 1550. It provides a broadband optical communication. So it connecting everything. Now digital communication is only possible with the optical fiber, because we know in digital technology the bandwidth requirements are more than the analog requirement. So optical fiber is a solution for that. So these are the different application areas of optical fiber. I mentioned major application is in the communication, but there are another application like optical sensors or medical equipment. Although they are not a major requirement, but they are also very, very important. It is all because of the optical fiber. So fiber sensors, it is an alternate, another area, an offshoot of optical communication research. In communication we have the problem, we have the losses, but these losses can be utilized for the sensing application. So sensors is the alternate school of thought for the optical fiber communication. So as a result, we have the high sensitivity fiber, and it is what we call a boon in disuse. So sensors is another area which has come out of the research in the optical fiber communication, and today optical fiber optic sensor they play a very, very important role in the smart structures. So all these are the sensors. I will just need a sensor. It is a device which measures the variations. So we see what is the variation in the light. Light is traveling. What is the variation in the light when it interacts with any of the outer media? So that is the basis for the sensing. So it can be used as sensing It can measure any physical parameter, strain, temperature, pressure, velocity, etc. Optical fiber is used as a media. So a strand of glass, so light which is traveling in the optical fiber, we know the reference light, we can see what is the output light, and we can have the comparison of two. So what changes has been taken place in between. That is the source for the sensing. So I can use any parameter of the light. You know, light, it has an amplitude, it has phase, wavelength, polarization, time. So I can have a sensor which is based on the intensity based sensor. I can have a phase based sensor, interferometry. I can have a wavelength based sensor, fiber Bragg rating, FBG. They are the wavelength sensitive. Similarly, you can have the polarization based sensors, gyroscopes, fiber optic gyroscope. They are from the polarization. So any change in any of the characteristics of the light can be good as a sensing medium, as a sensing parameter. So this is a spotting technology is only the fiber optic. We need a fiber, and we have to all see what is how the environment can be sensed. So the light, how it is affected by the different environment created. It can be a gas sensing, it can be a sound sensing, it can be a thermal sensing, any type of sensing, it can sense the environment. So the same technology is used. We have to modulate the light. So we have to see the change in the behavior of the signal. So the property of light involved in the fiber sensor, it can be tested by any of the means. So these are the type of optical sensor. It can be a extrinsic sensor where the changes takes place in the outer environment, or it can be a intrinsic sensor or fiber. So change is there in the optical fiber, like micro band sensing. You can create band over the fiber, and that changes the characteristics of the light. So extrinsic and intrinsic. Similarly, I mentioned intensity based sensor, spectral based sensor, interferometric sensors. All these are the classification of different sensors. Extrinsic, you have an input fiber, you have output fiber. The change takes place in the what we call the environmental signal. So it is different from the fiber. It is an extrinsic sense. You can put something over the fiber. So fiber is not a sensing media. Different environment is the sensing medium. Similarly, you can have intrinsic where the fiber is a sensing medium. Similarly, so we can measure all it has capability of all the measurement: rotation, acceleration, electric and magnetic field, temperature sensor, pressure sensor, acoustic sensor, humidity sensor, viscosity. Number of different types of sensors are possible. Whatever you think it is possible with because only I need a transducer. I need a transducer which change the physical parameter into some measurable parameter. So it is not a new area because sensors they were already there, but it added a dimension because now it is very thin sensor. We have optical sensor which are very bulky, but the optical fiber it's a very small. It can be embedded anywhere. So there are a lot of advantages. I mentioned the minimal environment, all extreme vibration, so they can work at high temperature. Whatever advantages are there with the optical fiber, they are possible with the optical sensor. So they are lightweight, they are small in size, they have high sensitivity. All these are the advantages with the optical fiber sensor. They are very important and now very useful also. So this is how the historical trend. Initially in 80s, there were very few sensing applications. Then in 90s, mass market emerges. We have the fiber gyros, medical application, lab instrument, and also different type of manufacturing based on the optical fiber. Then in 2000, so the cost is reduced. Initially the cost was high. Now cost has been reduced. Low cost compares to fiber optic system, the smart structure, industrial system. They have been evolved with the optical fiber. Then of course today you see fiber health monitoring, structure monitoring, oil and gas in deployment starts. Then similarly under our civil structure they are now use the optical fiber sensor. In fact, in some areas it is mandatory that optical fiber sensor has to be there. So lot of development will take place. We talk about the smart building, smart bridges, small structure. It means the optical fiber is the mandatory, fiber sensing is the mandatory requirement. A lot of development, lot of potentials are there in the optical sensing. This is the basic component. I already mentioned, you need a light source, you need an optical fiber, you need a sensing environment, and then of course detector. Same components are required which are there in the optical communication. Only the difference lies with the transducer. These are the sensors. They are very, very small. So you can use all these probes for different monitoring purpose. Similarly, they are in general used for measurements, for the monitoring purpose, for damage detection. They can be used for multiple functional structures or any environment. Any environment effect that can be conceived of can be converted to an optical signal and can be interpreted. So optical sensor, they provide the solution to different problems. Even one can also predict the earthquakes or landslides with the optical fiber sensor. You can sometime before, and you can tackle the problem. You can save lot of damages. So they are mostly used for the monitoring of structural engineering, say building and bridges. They are used to monitoring the tunnels, which are very, very expensive component developments. Similarly, dams, the foundation of dams, they need the optical fiber monitoring. Then, of course, hatchet structures. So optical fiber sensor, they are used because they are very thin. They are a general purpose. Only I mentioned you need the input and the output is monitored. What is the changes in the input signal that can be compared? You have a reference signal which is your input signal, you have the output signal. Compare the two. The change is because of the changing environment. So all these are different type of optical sensor which are commercially available now. So only point is I need a source, laser source, I need a reference beam, and you can put the probe in the medium or in the environment which you need to be tested. And then ultimately by the comparative electronics you can compare the two things. So these are the optical fiber. They are applied by the light system, aerospace, lot of applications. All our aeroplanes, there are number of sensors. Not only by this, you see, like airframe, such surface, structure of aeroplane, it has number of sensors. So all these health is monitored by the sensor. They check all types of the temperature, pressure, all wind flow, all the directions. Similarly, engines of the aeroplane, it has number of sensors. All these parts, optical fiber plays a very, very important role because we want the aeroplane system to be as light as possible, as thin as possible. So optical fiber is the solution. Optical sensor is the solution. Then see, this is from Mars to Manhattan, fiber optic sensor provides solution to our everyday problem. Lot of potential is there, and this is how NASA has evaluated, discover the power of fiber optic sensing. NASA designed fiber optic sensing technology offer a wealth of flexible options in a wide variety of applications. So optical sensor can be used everywhere. They are the solution to every type of problem. Not this only, they are the medical applications. Nowadays, optical fiber, they are huge use of optical fiber in the medical area. A doctor now, a surgeon, he can see each and every organ of the body. Inside, inside our body system, everything there is totally dark. But with the optical fiber, you can illuminate because fiber can reach everywhere. It can pass through the veins. It's so thin. And all this technology is there. They are very small, flexible, non-toxic, chemically inert, intrinsically safe. They can be put and they are low maintenance and easy to use. They are flexible. They can be molded in any form. So all the different application of the optical fiber and endoscopy. It is the invention of it. All depend upon the optical fiber. Today in the medical field, all type of endoscopes are there. They may be given different names, but basically they have the optical fiber. They have the light system and they have optical system and the light is used to illuminate the particular portion. They can now see the development, they can see physically what is happening there. So not only in the medical fiber, they are used lot in many other areas. Fiber is everywhere, in the textile industry, in the different type of development, illuminations, soils, all it is there for fiber. So lot of applications are there of the fiber. Not only in the communication, in the medical or in the sensing. Huge number of applications are there. Wherever any physical parameter comes picture, optical fiber can provide the solution. So number of applications are there, and in this program we will discuss different applications of optical fiber in mostly in the major areas, but there are many other areas where optical fiber has a lot of potential. So with this input, I will stop here. So I have just given the importance, the need for optical system, optical fibers, then potential of optical fiber in the area of communication, in the area of sensing, in the area of medical application. Thank you for your patience and your cooperation. So in case you have any questions,